Let's consider an example that might illuminate how we might use the scattering matrix to solve real microwave circuit problems. So in this case, we have a 3-port device, and it's a linear time invariant device, so we can characterize it with the impedance matrix or the admittance matrix, but instead we choose to characterize it in terms of the scattering matrix. And this is a very simple scattering matrix. All the elements happen to be purely real associated with them, and this isn't really very realistic. I just made the values like this to make the math relatively easy to do the computation. So you can think of these as sort of 9 arbitrary complex numbers. Again, I just sort of simplified the values to make it easier to do the mathematics. And generally speaking, those values are true as a function of frequency, so you can think of this maybe as the value of the scattering matrix at one specific test frequency. At any rate, it describes this 3-port device. We don't know what's inside the blue box. We don't really care. If we have the scattering matrix at the frequency of the oscillation omega, then we have enough to be able to analyze this circuit. So we look at this closely, and we find that on port 1 there is an incident wave incident on port 1. So some energy is flowing toward our structure from the transmission line at port 1. On port 3 we have a short circuit that's attached, and on port 2 we have a resistive load which is numerically equal to Z0, equal to the characteristic impedance of the transmission line. And so we have a matched load. Notice the indexes, Z1, Z2, and Z3. We have defined the index such the location of the port planes are all at Z is equal to 0, which again simplifies our mathematics. So what are we trying to determine here? Let's ask 3 questions we're trying to find the answer for. Let's say we want to find, in terms of the complex value of the incident wave, so this is the normalized wave amplitude at port 1, in terms of this value, again, we know this is numerically equal to that normalized wave A1 evaluated at the port plane, which by definition is equal to this. And of course, since we're evaluating at Z1 equal to 0, this is what simplifies the math. We know that is by definition equal to V0 plus. So V0 plus divided by Z0 is the value of our normalized wave A that is incident on port 1. In terms of this value, AP1, we want to determine the normalized scattered wave amplitude at port 1, this BP1, all right, the B wave, normalized B wave evaluated at the port plane of equal to 0, which would simply be equal to this. Now we have V01 minus divided by the square root of Z0. Likewise, for the normalized scattered wave at port 2 is V02 minus divided by square root of Z0. And also, finally, determine the incident wave at port 3. So this is another A wave. The wave propagating toward the device, specifically in this case toward the port 3. We evaluate that wave at the port plane for port 3, and if we do so, we would find that value would be equal to this, V03 plus. So this is again a plus wave since it's propagating toward the port, incident on the port. So we want to find out what are these 3 values in terms of this value. Determine specifically, I should say, these 3 values in terms of this one. So at times students are tempted to say, well, gosh, this is an easy problem. S11 is simply equal to BP1 divided by AP1. And so if I know S11 is equal to 0, I simply multiply this A wave amplitude, normalized wave amplitude, times 0 to get the first question answered, the value of BP1. And for the B wave at port 2, likewise, we can take the wave incident on port 1 and multiply by S21. That's given in the scattering matrix, right? It was 0.5, and that would be the value of this exiting wave or scattered wave B at port 2. And so we got this directly from the scattering parameters and did this math. But the important thing is that these statements here are completely incorrect. They're completely bogus. The value of BP1 over AP1 is equal to S11, and likewise this ratio is equal to S21 only if both port 2 and port 3 are terminated in matched loads, only if there's only one incident wave and that wave is on port 1. The problem is, of course, in this case, port 3, as we found, is terminated in a short circuit. Because it's terminated the short circuit, it will reflect power, and wave energy will propagate back toward port 3. There will be a wave incident on port 3. It is the wave that reflects off the short circuit that is connected to port 3. And so we cannot directly use these equations. They are invalid. They'd only be true if the other two ports are terminated in matched load. That is true for port 2, not true for port 3. So how do we determine the answers to these questions? Like any problem, we should start by writing down what do we know, what facts have been given to us, what facts are relevant. And from those facts, see if we can determine other facts, extend from that until we eventually get the result we seek. So the first thing we know is the results of our scattering matrix equation. We have our vector A consisting of 3 incident wave amplitudes at port 1, 2, and 3, and a vector B consisting of the 3 scattering wave amplitudes at port 1, 2, or 3, and they are related by the scattering matrix, which is given as part of the problem statement. So from this equation, we can explicitly write these results. 3 equations. One that relate the incident wave, the scattered wave of port 1 to the incident wave at port 2 and 3. The S11 is equal to 0, and that's why this term is independent of the incident wave on port 1. The scatter wave at port 2 we can write in terms of the incident wave at port 1 and port 3, and the scatter wave at port 3, that wave amplitude, that normalized wave amplitude, we can write in terms of the normalized wave amplitude incident on port 1 and port 2. So we have 3 equations here which relate our incident waves to our normalized scattered wave amplitudes. So in those equations, we had 2 other incident normalized wave amplitudes, 2 A values, one at port 2 and one at port 3. And again, we take the normalized wave amplitude, or normalized waves, incident waves, and evaluate the port planes. In this case, Z is equal to 0, and we get this result now for the normalized wave amplitudes at port incident at port 2 and port 3. So we count up all the unknowns we have. We have the 3 scattered waves. In addition, we have these 2 incident waves, and so we have 5 altogether. Now, what about the other incident wave, the one at port 1, AP1? Remember, that is the independent variable that we're trying to find the answer in terms of that value. So that's our source value that we're trying to find the answer in terms of. It's not an unknown, it is an independent value. We're trying to find B2, for example, in terms of that A1. So we have 5 unknowns that we're trying to find in terms of the one independent value, AP1. So we look at this, the scattering matrix gave us 3 equations, but we found we have 5 unknowns, and so what we're lacking are 2 more equations. We need 2 more independent equations to have the requisite number of equations for the number of unknowns. Now, where are we going to get these 2 more equations? Fortunately, we have 2 more devices, 2 more one-port devices in our circuit, and each of those one-port devices will provide a scalar equation, and so that will give us the requisite number. What are those other 2 devices? Well, on port 2 we have attached a match load. There is a device equation associated with that relating the incident and scattered wave amplitudes, normalized wave amplitudes A and B. Likewise, there's a device, a short circuit, and it will have an equation that relates incident and reflected waves as well. So each of these 2 devices have their own device equation. That gives us 5 equations in all. Once we've written those equations down, it's just a matter of algebra. So let's start with the device which is the match load that is connected to port 2. The load reflection coefficient for match load we know is equal to 0. And from that we can conclude that the normalized wave amplitude of V02 plus is equal to 0. And from that then the normalized incident wave amplitude on port 2 is equal to 0. Now, oftentimes students will mess this up and come up with a different result. They will tell me that the B wave, the scattered wave from port 2, is equal to 0. And why is that? Well, again, we've talked about this earlier. It depends on our definition of incident and reflected, and our definitions of plus wave and minus, or correspondingly A and B. The important thing here, as we've said before, is not to search around for some right equation, some recipe that you can throw the numbers in and get some other number. The important thing is to look at this circuit physically and understand what's going on and be able to write down the equations. The equations come from your understanding of the circuit. You don't find them anywhere other than inside your brain. That's where you locate the correct equation to use now. And so we know for a load that the reflected wave from that load is equal to the incident wave amplitude times the load reflection coefficient. And so the question is, what is the incident wave on this load, this gamma L? Well, the incident wave on that load is, remember, the minus wave. The wave incident on the port is the plus wave, and so the wave is on the load is the minus wave. And so the minus wave strikes the load, that match load, and then it creates a reflected wave which is propagating now in the direction of increasing z back toward the port, incident on the port, because it's reflected from the load. And so we know if it's a match load, the reflected wave, and it is a reflected wave, is equal to 0. That means that the plus wave is equal to 0. So in other words, the value that V02 plus is 0 is the correct answer. This is essentially the device equation for that load. Again, it's written in terms of the index set up for this particular problem. You can't just assume that the wave incident on that load is going to be the plus wave. In fact, when it's attached to a multi-port device with a scattering matrix, we have to define it such that the wave that is propagating in the direction of increasing z is propagating toward the port plane of the device and therefore away from the load. The reflected wave is the plus wave with respect to the load. The incident wave on the load is the minus wave. And so make sure that you get that straight in your mind. Again, a wave, the plus wave, is incident on the port because it's reflected from the load. The minus wave is scattered from the port, and therefore it is incident on the load. You have to make that physical understanding in your mind to get these equations correct. So we have a similar problem with respect to our last device, and this is a short circuit. We know the load reflection coefficient for a short circuit is -1, and certainly that's the case. We get that simply from the impedance of 0 and the characteristic impedance Z0. 0 minus Z0 divided by 0 plus Z0 is equal to -1. So this is unambiguously the value of the load reflection coefficient. Now the question is, how do we use this equation? And again, we can't think about it in plus or minus. We have to think about it in terms of the wave amplitude at the short circuit, incident at the short circuit, and the wave amplitude that's reflected from that short circuit. Is the incident wave the plus wave or the minus wave? Is the reflected wave the plus wave or the minus wave? We have to think about it carefully. Just like in the last case with the match load, we see with respect to the load, the wave incident on that load, incident on that short circuit, is the wave that is scattered from the port. In other words, it is the minus wave. And the wave that's reflected from the short circuit is the wave now that propagates back toward the port plane, and therefore it is the plus wave. And so this is the math that we have relating to the minus wave voltage at the short circuit. All right, the minus wave voltage is the incident voltage on the short circuit itself. So we take that incident voltage on the short and multiply by the load reflection coefficient, and that gives us the wave amplitude of the reflected wave, which based on the index for this case is now the plus wave. And so we find that the plus wave voltage at the port location is where the short circuit is connected is simply equal to the minus wave voltage times -1, 180 degrees out of phase. Remember, the minus wave voltage is the scattered voltage, or the scattered wave from the port, from port 3, and that wave exiting port 3, scattered from port 3, then propagates toward the load, and therefore the minus wave is the wave incident on the load, scattered from the port, incident on the load. So from this equation, we can come up with this result relating to the plus wave amplitude on port 3 to the minus wave amplitude in port 3, and we see they're of equal magnitude, but opposite phase, 180 degrees. And from that, we can then make a relationship between the normalized wave amplitude at port 3 to the normalized normalized incident wave amplitude, I should say, at port 3 to the normalized scattered wave amplitude at port 3. And again, they're related simply by a phase change of pi radians, 180 degrees. So now we have 5 equations. 3 equations that come from the scattering matrix, and then 2 more equations that come from our devices that are attached to port 2 and 3 respectively here. Now remember, we're trying to find the value of these normalized wave amplitudes in terms of the one incident wave amplitude at port 1. And so what we're going to do is take those 5 equations and simply divide them all by this incident wave amplitude at port 1, this AP1. And so now we have 5 equations. Our 5 unknowns then are the ratios of BP1 to AP1, for example, and AP2 to AP1, and so forth. And if you look at that, there are 4 unknowns, and I've tried to color code them: a red one, an orange one, a purple one, and a green one. At this point, it's just algebra. 5 equations, 5 unknowns. Go through and solve for each of the 5 unknown ratios. I suppose you could plug all this into a computer or calculator and try to let it give you the answer, but these algebra problems are not particularly difficult. You can go through and decouple them because I strategically made many of the scattering parameters equal to 0, and we have a matched load at port 2 so that the wave amplitude is 0. It turns out these 5 equations of 5 unknowns are relatively simple to go through and solve for. So, for example, we insert equations 4 and 5, the last 2 device equations, into equations 1 through 3, the scattering parameter equations. We get this result, and notice we have now 3 equations and 3 unknowns when we do that. And so with a little bit of algebraic elbow grease, again, we don't need to resort to calculators or computers there. That would make me grumpy. We can go through and find then these 3 ratios, minus 0.25, 0.4, and 0.5. From that, we could go back and determine the other the other remaining unknown ratio, which is this value here. It turns out to be a minus 0.5. So from these results, we can directly determine the 3 questions we ask, a question A, a question B, and a question C. The normalized wave exiting scattered wave amplitude of port 1 is 0.25 times the incident wave amplitude of port 1. BP2, the scattered wave amplitude of port 2, normalized wave amplitude of port 2 is 0.4 times that incident value. And finally, for port C, the incident wave on port 3 we found in terms of the incident wave on port 1. Remember, this value is non-zero because the device on port 3 is a short circuit, and so we have a wave that exits port 3, scatters out of port 3, strikes the the short circuit, and then reflects back into port 3. And so that's why port 3 is a non-zero value. And of course, these are all steady state solutions. Our sinusoid has been on forever and will be on forever. But these are the results.